Hello friends. So today we are going to study the most important topic in transistors. And if you understand this, then transistor is over. And the topic is the input and output characteristics of a BJT, bipolar junction transistor in a common emitter configuration. So what do we mean by input and output characteristics is this. We know the input circuit and the output circuit by now. So if I quickly draw this, so this is, let's say, a PNP transistor, and this is forward biased. This we call as the input side, input battery, input resistance, and basically this is the emitter here. This is the base and collector. So this part is input, and what is the output part then? This one. This is part of the circuit is called the output circuit, in which we have a battery and a resistor. Now obviously, as the current will flow here, because this current because of the forward biasing, holes will be diffused here and these holes will come here, so plus minus. So as we go from here to here, potential tends to decrease. So what we need is an increase in voltage, as you know very well, so that the collector based junction is properly reversed bias. So we require some battery, and we call this battery as VCC. This is RC, and this is connected here again, and then this is the circuit. So this is called the output circuit. Now what do we mean by input characteristics? Input characteristic means how does this input current, which is this base current, varies when we change this input voltage, or when we change the voltage across VBE we change, which is the voltage across the emitter and the base. So very simple thing, how does the IB varies with VBE? So obviously when we increase the voltage of this battery here, VBB, obviously some part of that voltage is dropped across this resistor, which is the external resistor, which we are calling as RB. But obviously some part of voltage will come across the emitter base also, and as we keep on increasing the VBB, then the voltage across the base emitter will also increase. So how does this base current varies, changes, depends on the potential difference across the emitter and base. That is called as the input characteristic. So as you know that this emitter base is nothing but a PN junction, and supplying a positive voltage of this VBE means nothing but a PN junction under forward bias. And you know how the forward bias characteristics are of a PN junction. So I have drawn here this IB versus VBE, the forward bias PN junction characteristics, IB characteristics. So until the cut-in voltage, there is very less current, as you know very well. We discussed this in diodes forward bias, and then the current suddenly starts to increase, and with the VBE, and this is it. So this is what is written here. So let's move forward. Now comes a very important point, and what is that important point is that, see, if we want to drastically increase this IB, for example, IB is in this level, IB1, and let's say we want to double it from here to, we want to make it like this double. So almost in making this IB double, how much we need to change the input voltage? So input voltage will change by actually a very small amount. That means this VBE, which is roughly around here, let's say 0.65, that it may go up till, let's say, 0.7 volt. So even for a slight change in the input voltage, which is the VBE, there is a good amount of increase in IB. So for different values of IB, the VBE remains almost in the same range of like 0.6 to 0.7 volt. Okay, but nevertheless we need to increase VBE slightly on changing the IB. So what we do is we define something called input resistance. Just like across a resistance, if we want to get a higher increase in we get a increase in current, then we require to increase the potential difference, isn't it? So similarly, we define the input resistance of a base emitter PN junction. So generally, how is the resistance defined? The resistance is defined as the increase in voltage required to get the increase in current. Same is the case with the input resistance of a base emitter PN junction, which is defined as the change in input voltage required, which is the change in VBE or VEB required, the change in the input voltage required to get a particular change in the base current. So that is what is input current. Now since we know that we get a good amount of change in current for a very small value of the increase in voltage, so this required is very small for a good amount of change in IB, and so that's why we say that the input current input resistance is very small, because not significant change in voltage is required to get a good amount of change in current. So RI is generally very small, and this RI is of the order of around few ohms to around few hundred ohms, not very much. You can just pause the video and go through it. Anyway, we are going to discuss this all the things written here in detail today, so I'm just leaving this as of now, so I will keep it separate here. Okay, we come to a very important concept of the load line and the operating point. This will be helpful in understanding further the input characteristics and also the output characteristics of BJT, bipolar junction transistor. Okay, so what is this concept of load line here? See, for example, we have a non-linear element. So what is the difference between a linear element and a non-linear element? So let me make it clear. So a linear element is an element like a resistance which follows Ohm's law, which means if you double the voltage, the current gets double and so on, and the IV characteristics of a linear element is always a straight line passing through origin. So that's what is called as the linear element, isn't it? Now we know that the diode or any PN junction is not following a linear curve for its IV characteristics. We know that the curve is something like this. So this is like a non-linear element IV characteristic, which means for example, if you have supply a voltage of around maybe let's say 0.5 volt, then you get something around, let's say 1 milliampere current. Just an example, don't take it as a actual value. Or maybe when we apply a 1 volt, then the current may increase to, let's say 4 milliampere, and then if I increase the voltage by a very small value here, and then the current will increase to a very high value, so the current will get doubled up to 8 milliampere when we increase the voltage by a very small value of, let's say 0.2 volt, isn't it? So this is called a non-linear element. Now let's say this non-linear element is connected to a resistance and a battery. So let's apply a Kirchhoff's voltage law across this loop. So let's start from A and go clockwise. So as we go across the battery, we get plus E as the increase in potential. Then we go around this minus IR across the resistance, and then across the non-linear circuit element, there is a potential drop of V. So we can say that E is equal to this E battery EMF is equal to IR plus V. So the total EMF of the battery is partially dropped across the resistor and partially dropped across the non-linear circuit element. Or we can say that this V, if we transfer this here, V equal to E minus IR. So what we get is a relationship between the voltage across the non-linear circuit element and the current through the linear circuit element, and this is the equation that is governed by the external circuit, which means what is external EMF applied and what is external resistance in series with this non-linear element. We can say that we can see also that this is a straight line, and so what if we plot this a straight line? So negative slope. So again we are plotting this I versus V. This I is this I and this V is this V, isn't it? So here now obviously this V is the voltage across the non-linear circuit element. It's coming out to be equal to E minus IR, where I is the current through the non-linear circuit element, and this V and I must satisfy this equation of the straight line like this, and this is the line V equal to E minus IR. But we know that according to the VI characteristic of a non-linear circuit element, it should also satisfy this condition, which is the voltage across it and current through it are governed by this curve, isn't it? So when we say that this non-linear circuit element should satisfy its VI characteristics, and also it should satisfy this straight line curve, So how can it satisfy both of these curves? So which means that this is the operating point, which means that this is the actual point, which means this is the actual current which is flowing right now, I, and this is the actual voltage across it. So this point lies both in the straight line, satisfies this, and also the IV characteristics. Now, what if we increase the EMF of the battery? So this V equal to E minus IR, you can say that when the battery EMF will increase, keeping the resistance constant, we can say that the slope of this line will remain same, whereas the y-intercept will increase. Y-intercept or x, anyway, both the intercepts will increase. So this is E1, E2, E3, and I guess this is the E1 here when the current is 0, E1, E2, E3. So obviously we can understand that when we apply a higher EMF battery across this resistance and a circuit element here, we should get a higher current, isn't it? Current should be higher for a higher value of E. As we keep increasing this E from E1 to E2 to E3, so how does the operating point shifts? Operating point shifts like this. So which is the intersection point of the straight line with the IV characteristic curve, isn't it? So we do get a higher EMF, higher current in the circuit. So these are the current I1, I2, I3, and we also get a higher voltage across the circuit element. So I hope you have understood the concept of this load line. This is called a load line, by the way. This line, load line. And this load line is governed by how much is the external circuit part, which means external resistance and the external EMF. Now, let's talk about forward bias base emitter PN junction here. And we know that the IV characteristic of a base emitter PN junction is IV characteristic means forward bias characteristics of a base emitter PN junction. So here we have the current IB, and here we have the current voltage VBE. So we know the input circuit, which is like this. Here we have a battery, PNP battery here, and this is RB. So you can understand that this circuit is exactly identical to the circuit which I have drawn here. This, so non-linear circuit element being here the PN junction here. So this is the emitter side and this is the base side. So emitter base, a battery and a resistance, a battery and a resistance. Doesn't matter whether we draw resistance here or here. Okay, so this is the VBB and this is RB, the external resistance, and this is the base emitter PN junction, and these are the characteristics. So when we apply, how about different load lines? So let's say we want to get a higher and higher value of IB, the currents. Then what should we do? We need to shift this load line, isn't it? And we are shifting the load lines parallel, because each of this load line has got the same RB value, external resistance in the circuit, because the slope is governed by this RB only, isn't it? You saw it previously also. So we can say that even to get a very high values of IB, the amount of increase in the voltage across the emitter base PN junction is very small, and it always remains range bound to around 0.6 to 0.7 volt, which means no matter what current is desired through the base emitter PN junction forward bias voltage need not be changed significantly. It always remains the same level. So this is all about the input characteristics of a base emitter junction in case of a forward biased in case of a bipolar junction transistor in common emitter characteristics. Okay, common emitter mode. Sorry. Okay, now what we are going to do is study the output characteristics. Now, to understand those output characteristics,